This is Mikko from Victory Foundations. Today we're continuing our process with the Terra module, where we create a new worldview based on grids and latitude-longitude coordinates. And today we'll be testing those, and we'll be refactoring those a little bit to have this new model type for these vectors in this grid-based world, so that we can easily convert between latitude-longitude points and the new surface area coordinates. So kind of to have the system match the other worldviews we have. So let's dive right ahead into the software and continue where we left off. So last time we just finished writing the grid area class, which transforms latitude-longitude coordinates into vectors. But we decided to use vectors as this kind of surface and aerial points. And if you can see, for different worldviews, let's say, for example, on the circle, we have like surface point over here. That's one class, and then we have the circle point over here, which is one class. Circle point is 3D, surface point is 2D. That's the difference. And on sphere, again, we have sphere surface point and sphere point, and these have different kind of mathematic utility functions. Well, these not so much. Or this has the circle point operations implemented, which kind of is used to calculate the distance between two different points using like arcing distance, direct transition distance, that sort of stuff. Also supports like moving with latitude-longitude based rotation. So basically we can add some new methods and stuff to our point classes if we make them. Because now we just used vector 2D and vector 3D, and they don't have any of these classes. And the most important method, I think, we get the world point ops, which had these plus and minus functions and distance functions. And then we have the world point itself, which has this lat-long function that converts the vector-based value into a latitude-longitude coordinate. So that's kind of neat, having this in the points instead of always having to call, your arc, grid area dot something, grid area dot something, transform everything there. We can just create our own models for that. So let's do that. So new package name grid. Let's add the grid stuff over there. And then let's just follow the process of having like grid point trait, common trait for, let's see, actually surface. So this is grid point is 3D, and this is represents world location in a grid-based model using 3 dimensions. Okay. Let's focus on the grid point after we get the surface point, because the surface is easier because that's in 2D. So grid surface point, I think, yeah. Correct with the naming scheme we have going on over here. This represents a point on the surface when using the grid-based world model. This is not the, because there are many grid-based world models, so it's a. Anyway. Nice. Then we need the point ops, but let's do that later. So, or maybe later. Let's again kind of pick the surface point in a circle-based system. It extends. Well, this is sphere, but whatever. Extends the surface point and the ops with equals. Okay. So extend surface point. Yeah, we have vector and aerial. So vector is 2D vector. These are from the paradigm module, which is like a module that deals with shapes, like these angle classes, rotation classes, vector classes, some matrix classes like affine transformations, things like that. That's the paradigm stuff. And then we have the aerial version, which is grid point. Okay. Then we see what kind of methods do we need. Vector and latitude longitude. Okay. Well, typically here, if we see the circle surface point, for example, the trait itself handles some functions, but then we have the different versions for kind of based on what's the input. Here we have the latitude longitude version and the circle vector-based version. So let's follow that same logic over here so that we are consistent. So we add a companion object here, create a surface point, and add some nested subtypes. Oops, nested. Here have private case class, something or other, like vector on grid. Let's call it something like that. Doesn't really matter. It's private. We have the vector form, vector 2D, and then it extends the grid surface point. And then we need to implement these things, but we also need the worldview. So let's add implicit worldview grid area. Okay, because the origin changes, so that affects the calculation. So latitude and longitude, we can calculate this lazily. So we don't need to calculate it when we don't want to do the conversion. That's the nice part of the lazy keyword. So that's worldview vector. Anyway, I think it was this, right? Yeah, this converts vectors to latitude longitude pairs, but we didn't do the conversion to other way around. Interesting. Yeah, so that's something we still need to do. So let's build that first. Let's just create surface point. Let's just add not implemented for now. To do. Okay, then move to the grid area. So here we transform a latitude longitude pair to a vector. So now we need a method that does the exact same thing except in reverse. So let's see if we can kind of reverse engineer this, so to speak. So let's add if guess we can, no. Let's, I wonder how I named these earlier, like circle. We have this lat long to vector and vector to length lat long. Sounds good. Oh yeah, we need to change these ones as well. So create area. Let's move this as well. To vector. We might have to even create a new trait for this sort of stuff, because right now we're repeating this for the third time. So there's really like a place for a trait to be added here that defines these methods so that I always use the same names, at least. And maybe someone who uses, well, will want to do that. So let's do that after we have finished this actual programming, okay? Lat long, okay. And then we have this vector lat long. So as a reference, we have this code over here. So then we need to determine the kind of the opposite thing. So what we did earlier was that, let's read from the bottom up. We have the vector. Then we calculate the latitude rotation, yeah, based on the vector length. Okay, then we get the simulated latitude rotation of the x, which needs to be then converted to longitude rotation. Or something, which needs to be converted to probably east-west arc length or east something. And then we need the y. Y should be easier, so maybe we start with the y. Anyway, we need like a reverse function for this one. So private def vector length to latitude rotation. So we have vector length double. So we need to reverse that. So let's draw simple algebra here. So now we have this nice function here, and we need to solve for, I think, this value over here. So what we need to do is we need to move this stuff over here. So let's divide by 100 first. Let dot increase equals vector length divided by 100. Oops. This 1 degree latitude vector length. Okay, so then we multiply by this stuff over here, this one, and we get lat decrease equals 1 degree latitude, the vector length, 1 whatever, times our vector length divided by 100. And now we have the decrease value, so we simply then transform this into a rotation instance of this stuff. Okay, let's see if it works. So we have So let's write again what we had there. We had equals 1 degree vector length times vector length, which is the input, divided by 100. So let's write that in Scala. 1 latitude degree arc length times vector length divided by 100.0. Well, that's easy. You probably don't need this. Just comment over here. These are not very readable, as you can see, but at least we have nice method names to describe what's going on here. We can always kind of validate these in the paper. Might be that I'm just wrong here, and we should have some sort of commenting going on, but for now it's what it is. So this returns double, so that returns the number of degrees, so then we just add rotation degrees of this stuff. Okay, so we return a rotation instance, so now we have like a perfect inverse of this function. Okay, so let's start with the y. Y was calculated by simply calling this function. So we should assume that the reverse is just simple, except that we're getting the position, not the latitude longitude. So let's see, vector 2D. Okay, so we get the y. No, sorry. Latitude. Oh, let's call north south position equals vector length to latitude rotation. And we have the vector dot y. Okay, nice. Now we have the y thing going on, then the x. And x was a bit more complex because we have to take into account the difference between, like, when you go north, the radius of the circle, of the east-west circle, gets smaller and smaller the further you go into the north. And at the equator, that's the largest. You know, assuming we're dealing with spheres, okay? So we had to do this sort of conversion. And if you don't remember if you haven't seen that, check the previous video if you want to. Right now I'm not going to explain it again. It was a lot of math and I don't want to do it again. But right now we can use that previous math and just kind of work things out in reverse. So what do we have here? We're converting. So basically we first need kind of latitude rotation of the x travel. So simulate the latitude x. That's maybe not the best method name or name, but you know, let's start with it. Vector the latitude rotation vector x. Okay. Then we need to convert this simulated value to the kind of real longitude degree value. So for that we need to calculate the arc length of, you know, how long of an arc this simulated latitude travel makes. So we make east-west arc length equals we have simulated latitude rotation of x, arc length over, and latitude we're always dealing with the mean radius, so boom, vector radius. Okay, nice. Now we're at here, and then we just convert it into kind of a degrees. So which amount of angle in the correct latitude level matches this arc length. Fortunately, we have a nice function for this. So east west position equals rotation for arc length east west arc length on the east west radius at origin. Okay, nice. So now we have north-south position and east-west position, and these are relative to the origin we chose. Origin we chose as the parameter of this function of this class here. So only thing that's necessary is to have the add that position to the origin. So origin plus lat long rotation let's see, apply let's try east west position, north south position. Let's see if this works. Seems to work. Okay, so now this returns a lat long, so really nice. We reverse engineered this function, but as you can see, lots of text, little code, little description of what's going on. So let's add some comments before we forget what we did. So converts vector length to latitude angular travel, then converts length x to latitude travel first, and then corrects all the difference in radii. I wonder how you write that, radii, maybe, between the latitude and longitude circles. Always dealing with circles. Okay, and then this is pretty, pretty self-explanatory, but converts from relative to origin space to relative to what's it called? Greenwich, England, and the equator. So 0, 0, lat long space. Okay. Now next time we come back, we may remember what we did here. So finally, let's add some comments describing the method. Grid-based vector into latitude, longitude coordinate vector in this grid-based system. Latitude, longitude coordinate matches that vector. Okay. And conversely, here rest coordinate into a grid-based vector. Latitude, longitude, coordinate. You know, one thing here, we could be using, like, instead of latitude, longitude, we could be using some sort of pairs of doubles, like latitude and longitude. But I found out that using a separate model for this helps so much, because you won't mess things up. Because double can mean anything, lat long always means decrease. And besides, this one handles for you the what direction is up, what direction is down, what's positive, what's negative, you know, north, east, south, west. Those can be really, you know, you can get so messed up with those. So I really recommend using this latitude longitude model instead of like just doubles, unless you're dealing with an extremely simple application. Anyway, so here vector and matches that coordinate in this system. These are always system specific. Okay, so now we have the function. That's nice. We can get back to the grid position, grid surface point function, class, whatever. And here we use view dot vector lat long. So vector. Okay. And then we need this function implemented later. And let's add separate class case. No, let's not make them case classes actually, because that implements the custom like equals function. But we want to make the classes so that they can be equal even though they're different classes. So that's why we extend here with equals by and add the equals properties, which is just the vector. Okay, vector format. So we compare these points based on their vector representations. We could use some sort of like testing to see if we're comparing to latitude longitude based points, but I think this is good enough. Of course, this actually it doesn't work, because if they're based on different grid areas, they shouldn't be comparable, never. So unless they are like equal latitude longitude, then they could be the same, but still they're not the same because they use different grid area. So let's add a new property here, an abstract property that needs to be implemented by the the class is implementing this trait. So protected if let's call it grid area. Okay, the grid system used to transform coordinates, I guess. Stupid comment. Sorry about that. We add vector and the grid. So if they have different grids, they're not equal. So we won't mix them up. That's, of course, you shouldn't compare, like, anyway, that's probably not gonna be a big deal, but let's call override grid as grid. So nice. And so now we have the grid there. Now the next, oh yeah, we needed to remove the case. So it's not a case class anymore. We don't want the, no, but we do want the vector, so we add override val, so it notices that, you know, this is the implementation. Pilot class lat_long on grid. Again, this version uses the latitude longitude. We use this so that we don't always have to convert into vectors when you don't want to. So we implement lat_long, and then we accept visit override all grid area, and we extend grid surface point again, like so. And again, we're missing the with altitude. That's okay. Let's add the vector lazily. Lazy vector. Grid lat_long to vector lat_long. Okay, a bit of copy paste, but just one liner should be okay. Okay, we're kind of, let's see if we made some sort of syntax error here because it's showing red. Lazy not allowed here. Okay, we're having some issues with some closures somewhere. Let's make sure everything else works first. Okay, that's good. So we did some sort of syntax error. Okay, wonder what we did. Private class. What have I missed? Something really stupid. Let's see. Oh, it's missing the val. Yep. Then let's add some functions so that we can create these. Create these points. So we want to create one based on vector. Create surface point. We don't want to expose the underlying class. To keep things simple. You know, they follow the same crate or interface anyway. Let's see, create area. Okay, that should be it. Yeah. Then the second one, apply long. Do similar sort of stuff. Okay. Converts vector into grid surface point. Grid to assume. Basically, grid surface point based on the vector. You know, someone could say I write too much documentation. Maybe. It's kind of a habit. But it's nice when you happen to forget something, you can always look at the documentation. So latitude coordinate. Then coordinate to convert. Okay. Based on the specified coordinate. Yeah. Kind of repetitious. We need to then go and deal with the three-dimensional versions. So let's do that next. Grid point. This is the 3D version. So let's start by extending 12 point. I guess it's aerial point. Vector and surface. So vector is 3D. And the surface version is grid surface point. let's see what we have here. Altitude, surface point. This one I think we can maybe make. Well, let's not yet do that. Vector, not long. Yeah, we probably don't want to implement any of those, but we want the same equals pi, and we have the same thing, which when you're dealing with same thing over and over again, you may want to have a generic trait for those. So let's see if we need that. Here we had the grid, so we could have like grid point. Maybe we add it to the ops. Well, for now we need to copy this, but we're probably gonna go back and refactor this later so that we remove the copy paste. Copy paste is not good, but since we don't have a common like superclass yet, we kind of have to use this. Okay, then we have same thing, check grid point, start with the vector version as vector over grid. Yeah, lots of copy paste. It's not a good sign. Point. If you have any ideas how to fix this, share in the comments. Altitude, latitude, longitude, and to surface point. Okay, let's add this other one as well. Lat long over grid. So override long, altitude distance, and then same thing. And then we do this. Okay, so at least now we have the basic class. So let's go back to the surface. No, we don't have it. Let's add the functions first. So applying, we have the vector 3D, and the implicit grid area. Implicit just means that I don't have to write parameter always. It just searches for any grid area that has been defined as implicit and places it here. So kind of makes this much easier to use. I don't have to specify the grid area every time. Returns a grid point. Again, we wrap, or we kind of hide these subclasses and just return a grid point so that the user will know what type of class is under there. But he knows the interface, so he can use it. Anyway, we throw a grid. Okay. And then apply, long, altitude, distance. And then the same thing. Except that this time it's not vector over grid, this time it's lat long over grid. Long, altitude. Okay. And then we need again comments. How do I want to do this? let's skip the comments for now. I'm having enough of writing comments at the moment. So back to grid surface point. You know, as you may remember, we missed earlier these two implementations, so now we can add them because we have the grid point class kind of ready, or at least, you know, not implemented but kind of ready. So when we add altitude to a vector on grid, basically we have two options. We can either convert that altitude into a z-axis, or we can combine that with latitude longitude and then use that. So here we probably want to convert it into a z value. So that's pretty easy. You just use the grid items built-in function. So we use grid point from vector, and we apply our vector 3D on vector x, vector y, and then we have the z, which is grid vector length of altitude. Okay, it's kind of like, you know, you could have this in the grid, just have some sort of z of altitude function. That may be better because this is more like model, less controller stuff. So let's do that. Even though this is like really simple function, let's go to the grid and add a function for that, so that it's more readable and easier to understand later. So let's add def altitude to z. Kind of redundant, maybe. I don't know. Latitude, distance, close. Oh, it's calling us. No, I don't like it. Let's go back. I didn't like it. It's like writing a method that just calls a method, does nothing else. Like maybe we can, you know, maybe we can just deal with having a function here. Just accept our fate. Here, on the other hand, because we have the latitude longitude, we're just going to combine it with the altitude. So grid point, left long, and then altitude. Okay, no, nice. So the surface point version is like the minimum viable product is now kind of ready. And then we go to the grid point and implement those missing methods. So start with the vector, latitude, longitude. But here we kind of want to, let's lazily have the surface version available. So private lazy all surface equals grid surface point of vector in 2D or something. Yeah. So we just drop the z and latitude longitude is surface left long, altitude. Here we need to convert the z coordinate into an altitude, so we just use grid dot distance of vector dot z. Okay, and when converting the surface point, we just return the surface. Why we just don't use this to surface point over here is that we want to catch the value so that we don't always create new instances. Then we have this latitude longitude version where we need the vector conversion. Do Do I want to go through the surface version? Probably. Probably, yeah. So we do implemented, and then we had a similar stuff over here, attributes, come on, attributes, writing, so difficult. Anyway, amazing surface equals surface point latitude-longitude value. Okay. Then we just return this one here, and then when we want to convert it into a vector, which we also want to catch, I don't know if this is the best way to do it, but we do surface with altitude. No, let's not do it like that. Let's convert. Let's convert to surface vector plus create that long vector, and then add the vector tree. This is kind of, again, we're repeating ourselves, so we're not the best. And then length of altitude, but maybe this will work. I don't know if we want to catch the surface. Maybe we'll just, because we don't use the surface thing anymore, so anywhere, so we can just create one. Kind of like I just said, I don't want to catch it. Oh, I want to catch it, but now I'm not catching it. So, you know, kind of deciding here. We can always change it. This is always kind of experimental. And I don't know if I'm correct or if I'm wrong, but we'll learn. Okay, so now we have the basic classes. Now let's go to the grid area and change these type parameters here. So we have the vectors and then the surface point and then the aerial point. And earlier we just passed the vectors as the surface and aerial points because we wanted to go fast and get it done, which I think was the right choice at that time. But now let's change it so that it returns these right new classes. So surface is grid surface point, and the aerial is grid point. Okay, now it should warn us that there's some trouble. So here we go grid surface point that long, like so. And then the grid we're using is this instance. So just this there. And then probably gonna just use grid point that long altitude. Okay. And again this. And then aerial vector, change that so that it's grid point. This is grid surface point, and just very easy. Just it's not vector, aerial vector. Oh, whoops. No. What does it? Let's go back. See, it doesn't override anything, so we wrote it the wrong way around. So this is grid point, and this is grid surface point. So these functions converts vectors to points. It's hard to read when both sides are vectors. Anyway, so grid point vector and grid surface point vector. Again, we have this and this. We could just actually do this. So let's do it. Private implicit null me grid area equals this. Like, let's just get def, I guess. So now, because we defined this implicitly, we don't have to explicitly mention it anywhere anymore. So we can just remove those and it works. That's the nice side of implicits. Of course, you have to be careful that they are not getting passed, you know, in wrong places. But in this case, this should work. So now we have a grid area world system that uses these new points, and we have the new point classes. So it's more according to the style of design we had with the other classes, and it provides a lot more utility functions. So next, do we want to continue and deal with the ops as well? I guess let's try adding the operations to our new models. So we had the grid point model, grid surface point model added, but as you can see with other types of points, we also have this ops class or ops trait. So let's see what's going on here. So we have the ops. It has this generic type parameter, type of vector, I guess, and the representation type, and it extends world point ops, kind of, which takes parameters of type of comparable world point, which in this case, this compares to anything that has a vector representation, and then the implemented type. Let's check that one as well, just soon. And what do we need to define? Well, let's go to this. I guess just it's the generic version of what we would be doing on the lower classes. So world point ops. This extends world point. Okay, we already do that. And then combinable. Yeah, so you can add rotation to it. That's okay. Then we had the distance calculations. This should be really easy. But the arcing distance, using arcing travel if applicable. I don't think arcing travel is applicable to grids. Do you think? No, grids are just straight. We already did flattened the curve, so to speak, when dealing with the east to west arcs and even north to south arcs, so no arcs anymore. So this should be easy as well. Then we add travel, compass travel. Again, should be easy. Rotation, compass rotation. Yeah. And minus. Yeah, I think we can do this. So let's start with the surface. Let's worry about this ops class separately. Let's see what's gonna happen when we extend that. So extend surface point with equals by with world point ops. So we have vector comparable point, and wrapper. Vector is vector 2D. Comparable point. I don't know. I don't know really. Where is it used? Distance calculations. Okay, basically we can use anything that has a vector form, or we could limit it to grid points. But since we went with that very generate option in the other way, let's use the same thing here and fix it later. So we have world point, which has any vector form, so it has double dimensions. Okay, has double dimensions just means it has x and y and z in double format. And then it equals by also grid surface point is the wrapper type, so the actual implementing type, I think. Okay, so then we implement stuff. We have equals properties over here. Need a lot more functions. Okay. Oh, we don't need a lot more functions. Let's see what we actually need. So we take the world point of stuff, I think. So distance from, like I said, this one's easy. That's grid distance of vector minus other vector length. So we're taking the vector representations and subtracting them from each other to get the distance vector between them, and then we just take the length of that vector and convert it into a distance. Distance here is just like meters, nautical miles, inches, feet, whatever. So arcing distance, even more easy. That's just same as linear distance, because we don't have arcs in grids. Then compass travel. Basically, compass travel, I think what it does is it has an axis and distance. Distance we will convert into vector lengths again, so grid surface point. Basically, we just modify the vector a little bit based on the direction. So let's see, we construct a new grid point, grid surface point here from a vector, which we get from vector plus we need to transform travel into vector. So maybe we need to, let's see. Now the axis. So we can transform that into x and y, but do we need to use match? Probably. Okay. So let's change this a little bit and do travel axis. Oh, it's 2D. No, it's but it has a 2D axis. Let's see how that is implemented to make sure we're not making a huge mistake. But compass axis has an axis, so let's see. For example, east to west, that should correspond with X. Damn it, it's Y. Why is it Y? Oh Y, oh Y. Why is this Y? East, west. That's like, always X. Oh, because latitude, longitude, or latitude corresponds with the first position, which is using X. Ugh, ugly. nasty. That's why we don't use axis. We use that's why we use compass axis. But we might be making a mistake here by using x, by using longitude as x and latitude as y when the axis value has been defined the other way around. So do we want to fix that? I think we want to fix that. Okay, so let's make longitude y and latitude x. I guess that makes more sense because latitude is the more reliable coordinate anyway. So here, instead of y we have x, and x we have y. I guess it's as simple as that. And we just switch these over. No, we don't switch these over, these are good. Okay, we just need to remember that remember to not mess things up in the comment side. So then vector that long, x, y, x, y. Yep. Is that as simple as that? East, west, north, south. Yeah, that's wrong. Good thing we did this. Because latitude longitude rotation, I think, takes like it should take latitude first. Yeah, latitude and then longitude. And here we just passed east-west, meaning longitude, and then north-south latitude. So good thing we came back. We made a mistake here. This is why you do testing. I get lucky sometimes, so find this out. But it's so easy to make mistakes here. So that's the problem, at least with me. Programmers typically tend to kind of be overconfident and think they don't make mistakes. Kind of like, yeah, it works, it's logical, it works. Then you make just a tiny error. Like in school, for example, I used to make so many errors in maths and stuff. Like I shouldn't be surprised to find errors here. If you catch errors that I don't catch in this development, let me know in the comments. You know, that could be very helpful. Anyway, so we switch the x and the y. There. And we have latitude. Yeah, correct way around. Then this is, by the way, also the benefit of using like centralized logic, like this grid area, because you can change one thing and it affects everywhere. Instead of if I had like, you know, like many programmers do, don't do it. Many programmers do copy paste. Like, yeah, it's just, you know, use double here and copy paste it here. Well, when you have to go fix things like this, you don't do it. Many people just don't do it because they know they have written that stuff in 100 places. And if they start messing things, it's gonna break. So it's good to do the diligent work of avoiding copy paste, which, as you can see, I haven't done everywhere, at least not yet. So, you know, so here we change the y-axis, which is the, let's change, matches the latitude, and longitude. Yes. Okay, so now we can say that the axis matches the latitude longitude, but I don't think it's good to make that assumption here. So it's back to grid surface point, and grid surface point. So compass travel. Maybe we need a function for this in the grid itself. Let's see. So we need to transform the travel dot compass axis into this x and y. So we might use the same axis or we might not. Let's take the risk and use the axis. We'll get trouble if that assumption is wrong. It's just that the syntax is so much better. So vector plus travel axis grid vector length of travel distance. Okay, and then let's make this implicit. Okay, so that we don't have to pass it around. So here, because we have in the axis class, we have this apply function that creates a one-dimensional vector. We can just add that vector to this vector and we get the resulting like modified vector. So that's why we use this .axis and took the risk, because it's so nice syntax. And here we just transform the vector length into travel distance into vector length, so that we're dealing with vector coordinates. Unfortunately, if you tried to do it without this conversion, let's say like this, it wouldn't build, because this is unit instance of distance and we want double. So that's also a benefit of using like specific classes or classes for different units, so you don't mix things up. Same applies to when you're doing physics calculations and stuff. Keep the units. Anyway, that's what I learned in school. So there, and then the rotation version. So in rotation, because we're adding angles, we have the option of either first transforming the angles into vectors and working that way, or we can add the angles to the latitude longitude coordinates, which already support that, and then just convert it into a vector. I think the latter one, while it might not be as optimal, is so much easier to write. So just use grid surface point, that long plus rotation. Like, ta-da, so simple. Anyway, that's it. We have some red over here. Plus. Missing that. Okay. Let's add it. So when we're adding not long rotation, did we just? Okay, I guess that's the same. Grid surface point, long plus another. Yeah. So yeah, now we have these operations for the surface vectors or surface, two-dimensional grid points, but we also want them for the three-dimensional grid points. So this is why we have the ops class. We don't want to copy all of this. Some of this, can be reused, and even we had this we already copied and this we copied, so we can refactor those as well. So let's start by copying everything. And creating a new trade, which is grid point ops. Okay, ops means operations. Common trade for grid area points, I guess. 1.0.1 extends world point ops. We have the vector changes, so we need the vector type here. Then we have the VP that doesn't change, so world point has double dimensions. This is just the same stuff we had in the earlier class. And wrapper that changes, so plus wrapper. Okay. Let's close this one. So okay. Then these. Let's add them as is. So we have the abstract thing that this remains as it is. Oh yeah, and with equals by, yeah, that one was common to both. Great. So what's happening here is we're taking everything that's common to both grid point and grid surface point and adding it to this one super trait. So we avoid copying stuff over by adding a common trait on top. So distance we haven't imported yet. Okay. Vector, I guess you can say the vector is something double vector like that is these operations. So that just means that we get the double vector operations active. These are from paradigm module, which is like plus and minus and stuff, vector functions. And by doing this, we limit this to vectors that have double values. So we cannot use, for example, distance vectors. We have to use double vectors. But that's okay because both the grid point and the surface grid point use double vectors, vector 2D and vector 3D. So that's why we can use it. And by adding that, we can implement these functions without having to repeat the code. So I think it's worth it. Then compass travel, let's import it. And compass rotation, let's import that one as well. And that long rotation. So now, now we cannot return a grid surface point because the other one wants to return a grid what's it called? Grid point. So we're returning a wrapper. So let's fix that. And then we also need to deal with this error. So we need functions for converting vectors and latitude-longitude points into surface points. So for that we add new functions. So detected def at lat long, returns wrapper, and then detected def at surface location vector 2D, I guess. Oh, well, we can't use vector 2D, we have to use as double dimensions, I guess. Well, it is what it is. Okay. So the new surface location to assign copy of this point and specify location. So the altitude may stay, but surface location should change. So sorry. Okay. Yeah. So instead of calling grid surface point, we call at. Okay, and that takes care of the build errors. So now we have a better one crate instead of two. So let's go ahead and implement that. So grid surface point, instead of taking its world point ops, we extend grid point ops. Okay, and what was the parameters? V and wrapper. So V and wrapper. Nice. And then we have a lot of overrides. It's a nice thing with this IDE. We can actually skip everything here. And well, cannot remove the whole class body because we need the add functions. So we use grid surface point, surface location, except that we vector 2D from, I think, from surface location. Okay, so convert it into the correct data type here. And then grid surface point lat long. Pretty simple. Yeah. And as you can see, just two methods instead of the whole stuff. And what's nice about it, I mean, right now we just moved the stuff to a different crate, make it more complex actually. But the nice thing comes when you go to the grid point, the 3D version, and go here. Like right now we have two properties and we don't have the operations active, but actually create surface point. Let's remove the equals by because that's already present in the grid point ops. So keep going. Anyway, so instead of equals by, we can add grid point ops. And here we use vector 3D and grid point. Okay. And then we can remove these because these are copy paste and just implement the add functions. So here we need to make a new version with this surface location. So that should be quite easy. Just use grid point and convert this into a 3D vector. So we have vector 3D surface x, surface y, and our own vector z. Okay, and then lat long, that's easy as well. Grid point, lat long, and altitude. Okay, so really easy, like by implementing these two very easy, simple methods, we got the benefits of the whole grid point ops and world point ops crates. So we can combine stuff, and if we want to add stuff, you know, it will, you know, add value in the future as well. So like here it really paid off that we created this separate crate. We didn't have to work very hard to get the benefits. Okay, so now we have added the new point classes, and we even have added the operational stuff to them. Next time we can perhaps test these. Maybe we can do it even now, or maybe later. Yeah, I think I'm getting a bit tired, so see you next time, I guess. Again, if you want to check the code for yourself, if you want to use this in one of your projects, check my GitHub at github.com/mikkomarjo/utopia-scala, and you should find the project from there. This is the Terra module, again, uses the flow module, which is the base module for all Utopia libraries. If you have any feedback, please comment, share this video with anyone who might be interested, and let's keep in touch. Have a nice rest of the day.